Okay, we're going to get going. Next speaker of the afternoon is me. I wanted to tell you about the theory of automorphic forms. Really, I wanted to tell you about arithmetic quantum field theory. Theory of automorphic forms, because we're having a program here about arithmetic quantum field theory. And so this seems like a good place to be. I wanted to kind of admit, I don't know if I can speak on behalf of all the organizers, but I just want to admit that I have no idea what an arithmetic quantum field theory is. So sorry, Dan, the program is already funded, but yeah. So you'll figure it out. We have 2 months. Yeah. So, right, yeah. Exactly. There you go. Yeah. So I don't really know what arithmetic quantum field theory is, but except you kind of know one when you see one, or rather Mignon knew one when he saw arithmetic Chern-Simons theory. And what I wanted to do is another example today. I wanted to talk about what Brian denoted A sub G. There's something that whatever an arithmetic quantum field theory is, should be one, which is the theory of automorphic forms. So what I'd like to kind of explain is some ways of thinking about structures in the theory of automorphic forms from a kind of perspective of arithmetic quantum field theory. And I'm also very bad at arithmetic, and I thought I scheduled myself for 3 talks. You'll see on the schedule there's the 4th one, and we'll probably cancel. I don't know. We seem off some way. So anyway, but today at least I want to talk about the theory of automorphic forms, and later in the week we'll talk more about the Langlands program. So what is an arithmetic quantum field theory supposed to be? Some things I've learned, mostly from Dan Fried. First of all, let's see what is it. Let's start with just the Q and the T. What is a quantum theory? So when we have what are some of the aspects that make something a quantum theory, we should have the basic issue is some kind of linearity. So we should have some vector space, usually a complex vector space of states. And we make measurements in this vector space. Quantum theory takes place in a vector space. Okay, that's my understanding of quantum theory. Well, really what quantum theory has is it has 2 parts. It has a vector space of states, and there's some kind of algebra, which is algebra of observables. So you need something to measure in the quantum theory, and you have an algebra acting on this vector space. You have a vector space with some operators that you're interested in. Those are observations you want to make. And you can calculate some expectation values, calculate some inner products, or spectral decomposition of these operators in this vector space. These are the kind of features we do in quantum theory. I won't get to this much today, but the way we typically construct these things is by some version of quantization. For me, I'm going to really start mostly with a quantum theory, but there's a process of quantization. So we construct these by a process of quantization, and they come with kind of 2 names. This is called the process of geometric quantization, and this is called the process of deformation quantization. Produce these 2 parts out of geometric data. And they usually are studied separately, but it's important for a lot of purposes to think of them together. So we'll get to this more later in the week. But that's sort of roughly what quantum theory means for me. These are the main players. Okay, now what is quantum field theory? So unlike the 2 beautiful talks we saw today, I'm not going to actually tell you anything about a field. I don't really know much about fields. What makes something a quantum field theory? So the letter F is a little misleading in that you don't always have a space of fields. You might study a quantum field theory without having a classical theory of fields on which you're trying to quantize. I'm just going to try to jump ahead into the quantum theory. But what makes something into a quantum field theory, and this appeared already in Brian's talk, is that there's some kind of notion of locality. In other words, we don't have just a single vector space of states and a single algebra of observables. We have some space-time. This is locality over some, let me call it n+1 dimensional space-time. So there's some place where we can make observations and we can talk about things that are happening in patches of space-time. And that's, for me, the central feature of having a higher dimensional quantum field theory as opposed to quantum mechanics, that there's some space in which you can do things locally. So not just a single Hilbert space, but roughly a sheaf of them or some structure. Brian is going to talk about structures of how to think about observables locally in space-time. and so on. So that's that's for me what quantum field theory roughly is going to be about. And so the way this is often encoded on the level of states, this locality is, as again, I and a lot of people learned from Dan Fried and Bayes Dolan, Lurie, and many people, the way the structure of state, well, I should say Atiyah and Siegel, the structure of states is encoded roughly by saying that, say, if I have a D manifold, I'll attach to it some vector space, usually Hilbert space. This is going to be the vector space of states at a fixed, I think of this as a slice in fixed time. This is a quantization of the theory at a fixed time. But what makes this richer is that I can now go, if I have a codimension I told you my arithmetic was bad. Wait, and n was, yeah, okay, yeah, all right. Okay, so we have an n plus one dimensional field theory. This is the dimension of space, is n. If I have something in higher codimension, then I'm going to attach to it a category. This is the kind of structure that appeared again in Brian's talk. You might decide to go even further and attach to some kind of two category. And these kind of structures are encoded in some very elaborate cut and paste algorithms. So this is a way of encoding the locality. You take a space and you cut it up into pieces, and you figure out what to do on the boundaries of these pieces using these lower data, and there's natural gluing laws. So that's the Atiyah, Siegel, etc. axiomatics for the theory of states. So I'll give a little bit of examples of this. That's the kind of flavor that appeared already again in Brian's talk. And for the theory of observables, again, Brian mentioned some of the relevant words. The kind of observables I'm going to focus on are the observables now can be localized. Can also live in space-time, and the ones that I'm going to be interested in are as what are called defects of various dimensions. So we can think about algebra operators that are extended among submanifolds of space-time of various dimensions and see how they interact. So again, I'll see how some of these things play out as we go on. But this is, for me, the basic features of a quantum field theory. Some kind of algebra of observables that depend on geometric data, some kind of collections of theories of states associated to manifolds of different dimensions. Okay, so that's what QFT is. Now, what is arithmetic quantum field theory? And again, I should maybe say that the only kind of arithmetic quantum field theory that I know anything about is some kind of topological quantum field theory. So our notion of a space-time are now going to be really manifold. We're not going to care about extra structure like metrics. So I don't really know what those would be in the arithmetic context. But we're going to think about, so this is a theory of topological quantum field theory, meaning our space-times are just manifolds without extra metric type data or conformal structure. So what is an arithmetic one? Sorry? Yeah, they will definitely, things like spin structures, orientation structure definitely will make sense, as I think will come up in Minyang's talk. The basic objects that we're going to care about are non-orientable. So you're kind of forced to deal with kind of unoriented field theories. But yes, tangential structure certainly. Yes. Unfortunately, I don't really know arithmetic versions of oriented, but yeah. So what does it mean to have an arithmetic quantum field theory? The basic ansatz here is that we're going to expand the world, of manifolds, what we think of as our input for the field theory, to include these kind of arithmetic objects that appeared in Mignon's talk. We're going to take this analogy to heart, and we can say that there's kind of more to include more kind of arithmetic objects. As inputs for the field theory. Yes, so let me yeah, so the kind of objects I'm going to allow, I'm going to say more in detail, but the kind of objects I'm going to allow is I'm going to I'm going to maybe mention one manifolds in one sentence, but mostly I'm going to talk about 2 and 3 manifolds. And the arithmetic notions of 2 and 3 manifolds are, so if I take F to be a global field. So this means, a number field, a finite extension of the rational numbers, or a finite extension of, look at field of rational functions. Let's say field of rational functions on some curve sigma over, I take a curve over a finite field and I look at the field of rational functions on that. And then I'm going to think of, if you'd like, spectrum of the ring of integers of this as a three-manifold. So I mean, I want to say, I think of a number field as a three-manifold. Again, this analogy that goes back to Mazur and that Mignon explained. Really, if you'd like, in this case, I don't need to say spec. I would just say, I think of a curve, a smooth projective curve over a finite field as an example of an arithmetic three-manifold. Okay, that's part of our repertory. I'm going to be super sloppy about thinking about, I don't understand anything about Archimedean places, so I'm not going to tell you how to kind of complete this. And so most of the things I say can be made relatively precise in the function field setting and maybe more kind of aspirational in the number field setting. But so that's a kind of examples of three manifolds, and the kind of examples of two manifolds. Well, we're going to, an example of a two manifold will be a curve over an algebraically closed field. Smooth projective curve over an algebraically closed field, for example, the complex numbers, or you could take one of these guys and base change it to an algebraic closure. Those are good two manifolds. And another a good two manifold would be something like the form FV, which is a local field. So a local field would be something like, so this is a finite extension of, say, the real numbers, which I know nothing about, or the p-adic numbers, or a function field. Okay, so these are examples of two manifolds in this world. So the idea of the arithmetic field theory is we're going to extend quantum field theory to allow these kinds of objects and maybe a few more, and try to understand to what extent we can use these and as a base for quantum field theory. Yes. These are two manifolds. Yeah, so these are all two manifolds. Yes. Between so this is the three manifold. These are two manifolds. No, I think, this, for example, if you're these guys, you should really think about as two manifolds that are like fibered over the circle. In the usual world of Riemann surfaces, there are not a lot of Riemann surfaces fibered over the circle. So these kind of look like twisted versions of T2 in some sense. I mean, except that the fiber is much more interesting than a circle. It's kind of very complicated. But these are some kind of, I mean, yeah, these are some kind of Klein model, right? Exactly. The real number one is somehow in some sense analogous to the Klein model, and these are some kind of P versions of Klein. This would be yeah. I haven't said anything about the quantum field theory itself. All I've said is what are the manifolds. So these are, yes, so these are examples of two manifolds. These are examples of three manifolds, and then I'll plug them into various machines. So I haven't told you about the machine yet, right? I'm just saying this is the setting. I don't remember what n was, but yeah, okay, 3. N was 3. There we go. Yes, exactly. N is 3. Good. Now, so this is the kind of setting, and so what I'd like to do is try to think about the theory of automorphic forms, which a lot of it, takes place in these settings, from the point of view of arithmetic quantum field theory. And this starts as some kind of a good bedtime story for your kids or something. It's a little bit of a fairy tale, but the hope is that as you go along, you build more and more analogies and more structure so that the tale kind of gets a life of its own. So I hope to convince you that this is a useful way of thinking about structures in automorphic forms. Okay, so okay so far? Okay. So what I'd like to, so now what are automorphic forms? There's, again, many different variants and flavors of the space of automorphic forms. I'll be very schematic, especially in the number field setting, to make more precise statements here. The kind of idea is, again, that I want to think of it as a linearization. And maybe just pause. This is where the quantum aspect already comes in. When you're studying theory of automorphic forms, there's already something linear. And linearization, depending on who you are, might be do some kind of L2 functions. It might be some cohomology. There's various variants of spaces of automorphic forms, but they're usually linearizations of arithmetic locally symmetric spaces. So what is arithmetic locally symmetric spaces? These are things of the form like the, I don't know, I'm supposed to draw this picture here. So this is supposed to be a picture for the upper half space mod PSL2Z. Okay, that's a fundamental domain picture. And this is supposed to more generally remind you of, I write symbols like this. I write things like G mod K mod gamma, where G is maybe a real Lie group, and this is a compact subgroup, and this is an arithmetic subgroup, a lattice. So generalizations of this situation, maybe a bit more, I don't know, democratic to think about these guys as adelically, but let me not spend time on the adelic formulation. So you look at an adelic, G of an adelic of adels modulo. G is going to be I mean, I think it's best to think of G right now just a real Lie group. Take your favorite real reductive group. Take SL2R. So this is right. This is SL2R. Maybe I'll get the P's off, but SO2 mod PSL2Z or something like that. And replace SL2 by some other Lie group. So there's a whole lot of these arithmetic locally symmetric spaces, and the theory of automorphic forms studies their linearizations. And they study their linearizations. I mean, this is probably a big disservice to the theory of automorphic forms. A slightly less big disservice is he studies these linearizations with as a module for a big algebra of operators, which are Hecke operators. So you study the linearizations with the action of Hecke operators, which can be defined in any of these different contexts. And this is already makes, there's a very big subject of thinking about the theory of automorphic forms as some kind of quantum mechanics. Here's a Hilbert space, or vector space, together with some observables. And we can try to understand in what sense this is something like a quantum integrable system or various other things. So the quantum mechanical way of thinking is very built into the theory of automorphic forms. But what I'd like to do is try to think about this, as I said, as from arithmetic quantum field theory, not just quantum mechanics. So what I want to say is, what are the variables here? So maybe this better to answer Greg's question. There's somehow more. So right now it looked like a whole big mess because there's a lot of different Lie groups I can look at and with lattices in them. There's a way of organizing this for which the theory of arithmetic jump topology gives a good model. So let me fix some group G. So G is going to be a reductive group, and to make my life very kind of easy and clear, let me say it's a split group. It's a group over the integer. So I just don't have to think too much about structure theory of groups. So this is the kind of thing we have letters for, right? This is GLN, PSLN, E8, I don't know, SON, these kind of things, right? So we take one of these favorite symbols, and that's going to be a fixed thing that I'm not going to mess with. Maybe later we'll mess with it. But right now, we're going to fix this group, and I'm going to try to build a single theory, a single quantum field theory, A sub G, associated to this data. And that's supposed to capture all the theory of automorphic forms associated to this G. So how is that going to be? Okay, so the idea is that if I have, so given any arithmetic three-manifold, okay, I'm going to the theory, and let's call it maybe M. We're supposed to spit out a G of M, which is going to be a vector space. This is going to be a vector space of automorphic forms, a G automorphic forms on M. Now, so first of all, to step back for a second, I'm trying to define an arithmetic quantum field theory, but I never told you the dimension. Maybe this was the question, what is N? So this A sub G is trying to be, I used to call it 4, but I think it's better to call it 3 plus 1. So it's a 3 plus 1 dimensional arithmetic quantum field theory. So what does that mean that it's 3 plus 1 dimensional? Well, okay, 3 plus 1 does equal 4, but here my spacetimes are going to be these arithmetic three-manifolds and below. Like Min Yang was saying, I have no idea what an arithmetic four-manifold, an interesting arithmetic four-manifold is. So the fourth dimension is going to be just time. So that's kind of here. We're going to have a notion of time, and there's not going to be something super interesting going on in that dimension. But the point is that I'm going to be mostly focusing on arithmetic 2 and 3 manifolds of the kinds we were just discussing. And I'm going to attach outputs to them. So because I'm doing a 4-dimensional theory, the attachments to a 3 manifold should be a vector space. Okay. All right. Yes. Yes.
When you have like n plus t, or maybe it was n
Yeah.
minus t or something.
Yeah.
Was there anything that, how was the d input?
I think I was just mixing letters in a coherent way. I'm saying there's a dimension of a field theory. If I have a 4-dimensional field theory, it should attach numbers to 4 manifolds, vector spaces to 3 manifolds, categories to 2 manifolds, 2 categories to 1 manifold.
So the n.
Probably. Yeah. Yeah.
Well, that's why maybe you're right. You wrote n minus t.
Yeah.
There is no fair 5-dimensional thing.
I mean, I would love to. I mean, yeah. So it would be interesting to have. Yeah. Well,
The formal structure only depends on the sum.
No. So you fix a dimension.
I only know it was on that board.
Yeah. I think there was. I don't think there should have been 2 indices. I think I meant D and N should have been the same letter.
Okay.
I just mean I fix a dimension of the field theory. And now that is a machine that you give it inputs of any manifold of dimension less than or equal to that. And it gives outputs of different flavors. Okay. So here, from now on, you know,
In this context, we can't input one.
you could have dreamt of, and you ought to expect get a number. For a 4-manifold, you ought to get a number. And for example, the trace formula will appear as an output on a 4-manifold. So those numbers do appear in number theory, but I'm not going to talk about them. Yeah. We're going to have boundary theories. That's going to be kind of the main point of this week is talking about boundary theory. So we'll have interesting ways of constructing states on 3 manifolds. Yeah. They are, you know, dreams of, you know, we want to be friendly and relaxed and think of them as being. So they're objects that we're calling arithmetic 3 manifolds. I don't know of a definition of an arithmetic 3 manifold. Mignon told us some features of what there's some objects in number theory, namely number fields and function fields, which behave like 3 manifolds in some important cohomological ways. It's much less than that. And unfortunately, you know, I'm not going to be able to tell you what a Bordism is between arithmetic. There's very little I know. The claim is that very little is already enough to say to see interesting patterns.
But how do you know it's 3 manifolds?
That is a great question. Where does 3 come from? And that 3 comes from the form of Poincare duality. So there's in Galois cohomology, there's Artin-Verdier duality, and there's a fundamental class in dimension 3. Unfortunately, it's not a trivial. It's some twist, which it's a non-orientable. So it's like, look, it behaves like a non-orientable 3 manifold. But there is a version of Poincare duality which is where this analogy really comes from. Was it? Okay.
So what you had in the board before was actually the n plus 1 dimension. Because for Mn, you wrote attach a vector space to M.
Yes, that's right. That's right. Yes, absolutely. Thank you. Yes, that's right. Exactly. So my focus is going to be on 3 manifolds and 2 manifolds, but my theory is 4 dimensions, which magically works well with the things in physics where 4-dimensional Yang-Mills theory is something extremely interesting. And this is going to be some kind of model. So for the physicists, this theory is supposed to be a version of the A-twisted n equals 4 super Yang-Mills, 4D super Yang-Mills. Yeah. Yeah, I just mean the following. There's a lot of statements, as you mentioned in your talk, like, you know, when you cross with a circle in field theory, crossing with a circle has a well-defined result in field theory, which means take a dimension. So the basic thing in the trace formula is, if you like, take the dimension of the space of automorphic forms. Now, that's not terribly well defined, but that's what the trace formula starts with. More generally, you can take trace of an operator, trace of a Hecke operator. That's what the trace formula discusses. And those can also be defined as some kind of partition functions of decorated 4 manifolds. So the geometry of 4 dimensions is basically a circle, but you can interpret traces of Hecke operators on space of automorphic forms as being the values in some 4 manifolds. It's the GL twist at psi equals 0. So Witten came with that terminology, so I'm backed up. But yeah, it's a psi equals 0 and n equals 4 in the GL twist. Okay, so so what is this space? And let me say the kind of features of what. So this is the space of this idea that I'm going to look at the space of automorphic forms, and the space of automorphic forms has various variables in it. There's many variants of space of automorphic forms, and what I want to claim is the main variable is going to be captured by an arithmetic three-manifold. So for now, number theorists, pause for give me a little moment here. I'm going to think of unramified. So I'm ignoring the level at this point. I'll return to levels later, but I'm thinking about a space of unramified automorphic forms. Okay, so what does that mean? So it's, again, the place where I know how to make sense of it best is if I have a curve over a finite field, then what I should be studying is I look at the moduli space of G bundles on this curve. Okay, look at bundles for the principal bundles for the group G on this curve. I look at the FQ points of this, and I look at functions on this space, maybe compactly supported functions. And I don't like writing functions, so I'm going to write cohomology. I mean, it's this kind of discrete thing, but it's kind of stacky. So the cohomology here, you should ignore it. Just think of these as complexly supported functions on this set. So that's what unramified automorphic forms means. In the arithmetic setting, I'm going to again look at, so again, as I promised, I'll be less precise, but if I have a number field, we'll have this kind of space that people tend to write with some kind of symbols like this to not say exactly what they mean. But roughly what this means is I take my group G. G is a group over the integers, and I take the G of F, but I take, let me write them some annoying symbols. So I take a real Lie group, and that real Lie group is determined by my group G and my number field, okay? And this will have some lattice, which is G of the ring of integers. And then I'll mod out by some maximal compact, some level thing. So this is kind of the arithmetic, this is the kind of a formula of getting arithmetic locally symmetric spaces. For example, if you have an imaginary quadratic field for SL2, you'll get something like a Bianchi manifold. But anyway, this is a general formula. This is just to say that the variable you have when defining arithmetic locally symmetric spaces involves a G. It also involved all these extra data, but basically, I get one data associated to every number field. Yeah. Oh, yeah. So this is the space. That's analog of Ben-Zvi. And then I'm going to look at functions here. And again, I have to be careful what kind of functions. Let me look at cohomological automorphic forms just to.
I'm confused by the. Oh, okay.
Okay.
I'm confused by the FQ though. Can you just say what the definition is again?
I'm just going to look at the set of points of this. I have the stack of G bundles over the algebraic. I look at this FQ point. Yeah.
But then you take the comma.
Yeah, I could call it. Let's just call it functions. I mean, it's a discrete set, but maybe there's some stackiness. But otherwise, let's just call this functions.
So you're not taking the cohomology.
I will later, maybe, but right now this is the space of everywhere in ramified automorphic forms for a function field. And this is a version, the space of cohomological automorphic forms. Again, maybe I should look at algebraic automorphic. There's various variants, but this is the kind of vector space I want to attach to my arithmetic three manifolds.
So you would not stack it.
Yeah.
Definitions would be.
Yes. Yeah. Exactly. So this is so what have we gained so far? We haven't gained a whole lot. We've just gained the idea that you can organize the space of automorphic forms, again ignoring issues of level, just by a number field, and I'm calling or a function field. I'm calling that number field or function field a three manifold. So that's all that's happened so far. Good. Great. Now. Next, while we're at it, let's go to two manifolds. Okay. So what should I do for two manifolds? So for two manifold, I'm supposed to attach a category. So there's really two sources of this historically, and they've recently merged. So I don't know which one to start with. Maybe let's start with number theory, right? In the theory of automorphic forms, the basic thing you study in the local Langlands program, the local version of the theory of automorphic forms. So suppose I have, let me call FB be my local field. So again, let me think of QP, the real numbers, or it could be a characteristic P function field, local field. So given what do you study? So in the local Langlands program, the basic object of study is not usually said in a categorical way. People will tell you, I'm interested in irreducible representations of a p-adic group. But if you just forget the word irreducible, you say, I'm studying representations of a p-adic group, and those form a category. So here I want to say that this should be, look at the category of representations of, I have my group G, I look at it over this p-adic field or the real field, I look at representations of it. Maybe I put some adjective like smooth representations, just to know what I'm saying. So this is a category I want to attach. And this theory of automorphic forms should be roughly this category. Okay. So this is a classical object that appears in representation theory, the smooth representations. For example, just to give an example, I could look at, I don't know what my field of coefficients is. Let's say, let me call it C for fun. Look at complex valued functions on a coset space. So this is an example of a smooth representation. Take an open subgroup, for example, G of the ring of integers. Take a compact open subgroup and look at the quotient space. So, or something like a flag manifold. Look at functions on that. That's an example of a smooth representation. Yeah. Yeah, it's supposed to be contained in. So what I'm trying to hint at, this is not the full answer. This is the classical answer. It's not the best answer. But you know, the initial answer, you'd say, well, in the Langlands program, the local theory, you study representations of a p-adic group. Okay. Now, why am I hemming and hawing about this? There's another class of two manifolds, right? The other class of two manifolds might have been just a two manifold, right? If I take a Riemann surface, let me just emphasize sigma bar. Say if I have a smooth projective curve over an algebraically closed field, that's a good example of a two manifold. And this is the setting of the geometric Langlands program. So this appeared in Breinstock. So in this setting, there's also a category you attach. That category has a different flavor. It's defined as a category. The nice thing is it has the same symbols appearing. You look at the space of G bundles on your curve, and you linearize it. I want to linearize it, but not to get a vector space, to get a category. And so let me just write the word sheaves here. So look at category of sheaves on this. Now, there's several flavors of what kind of category. There's kind of a Betty version, a Dram version, and kind of an Étale version. Some kind of Hodge theoretic notions you get to choose what kind of theory of sheaves. But there's several variants of this construction, but that's beyond our level of resolution. Okay, so everyone happy with the letter sheaves for now? Imagine constructible sheaves if you're like constructible lattice sheaves, or D modules. The D modules is what appeared in Breinstock. So this is the category we could attach. And the beautiful thing that's happened in the last decade is that these two have kind of merged. So there's a long history here. I want to mention Vincent Laforgue's work and Xin-Wen-Zhu's work. And there's a lot of people who've done a lot of interesting related things. But if I just have to write one reference, is the work of Farg and Schulze told us a version of this category, a bigger version of this category that really looks like this. So what they really tell us is the full thing you should attach to this two manifold should just be sheaves on bund G. Okay. Now you have to decide what is bund G. So the point is that there's a curve here called the Farg-Fontaine curve associated to your local field, and that curve kind of is a geometric embodiment of this two manifold. So in some sense, this arithmetic two manifold corresponds to an honest two manifold, which is the Farg-Fontaine curve. The Farg-Fontaine curve is an actual geometric object we should think of as being the two manifold here. And it has a bund G, and you could look at sheaves on that bund G, and that sheaves contains this category inside of it. It's much bigger, but it contains this. And it's somehow the right local version for the theory of automorphic forms in various sense. And right in many ways, in particular, now everything kind of feels much more uniform. Okay. Yeah, I mean, very naively, roughly, this bund G kind of looks like bund G of P1. So it looks like it's stratified, with a discrete collection of strata, and you have an open stratum, and that open stratum roughly looks like point mod this group. And so sheaves on it just look like representation of this group. So it's basically the top piece in some. So yeah, it's very easy to recognize them. Yeah. Okay. Yeah, so the P1 in some sense is the complex analog. There's a real version, this twistor P1, which plays the role for the Archimedean plays. So the Farg-Fontaine curve is some kind of version of P1 or of twistor P1. It's a curve whose fundamental group is the Galois group. So local systems on it are Galois representations. Okay. Okay, so that's the, okay, so that's the kind of picture. So we've got three manifolds, we have two manifolds. Let me just mention very briefly one, I don't know a lot of one manifolds. One manifold you could study, I only know geometric ones, is you could study a punctured disk. It's a version of the circle. Maybe you could think of spec of your favorite, algebraically closed field Laurent series of T. That's an example of a one manifold. It's a version of a circle. And in that case, there's a subject of local geometric Langlands. The local geometric Langlands attaches some two category to this data. And it looks very similar. You look at G of this field. So that's some version of a loop group. And you look at representations of this, but representations on categories. So this is a thing. Might take a while to motivate why it's a thing you care about, but it is a thing one cares about a lot in geometric Langlands program. And it plays a role of a two category. That's an example of this extension. Yeah.
And like here, when you went down to two-dimensional case,
Yeah.
you said, well, we're not just going to look at like space of the functions.
Yeah.
Like space, we're going to look at representation of something,
Mhm.
right? But you could have done it in three-dimensional. Like you could have looked at category of representations of
You could. I mean, well, I think you'll probably tell me better, but automorphic. But we're not interested in representations of the GFT. We're interested in automorphic representations, and those don't form a really interesting category. So I think the interesting structure there is the spaces of automorphic forms and their spectral decomposition and so on. There's a lot to say. Of course, we're not done with automorphic form theory yet, but there isn't, I think, an interesting category that I know associated to a three manifold.
Also, what if I do something like I take a smooth curve with over Z bar? Is that going to be a three manifold?
Yeah, so there's Pavel Ettingoff will give a talk in our conference in late March about this analytic Langlands theory, and where you have, I don't know if that appears, but his work with Kazhdan and Frenkel. There is some more stuff, just a curve over. Yeah. I don't know. So I think, Barry Mazur and Tony Feng and Dennis Gates have been thinking about trying to do Iwasawa theory. I was giving another example of an arithmetic two-manifold. But there should be lots of other interesting arithmetic manifolds of other dimensions. This is already more than I know about, so let me back up. Okay, so I'd like to kind of convince you that there's structure of, so far I've just given these guys names. Now, what makes this a field theory? One natural question would be, can I do Bordisms? There's very little known of Bordism type results. I think the best kind of Bordism type pictures in this, there's results of Nadler and Yun about kind of gluing theorems for these automorphic categories that kind of have a flavor of a Bordism, a kind of Bordism statement. I mentioned them, and so let's not. The kind of maybe one of the kind of thing, we don't know how to do Bordisms, but one thing we can do, and appeared again in Mignon's talk, is cross with a circle, or more generally take a twisted cross with a circle, take a trace of Frobenius. And so there's a kind of, the picture again, let me draw something that appeared in Mignon's talk. If I think of a curve, this is supposed to be the picture of a curve over a finite field. Curve over a finite field, you should think of as a fibered three manifold, where this is spec of the finite field, and the fiber is, this is my sigma bar, my curve over algebraically closed field. And so again, we think about the curve over a finite field as mapping torus of the Frobenius. And there's these beautiful theorems, again, going back to, I should mention the works of Laforgue and Xinwen Zhu, and then I'm running out of time, so I'm just going to write A, G, K, R, R, V. This is Arinkin, Gates, Gori, Kazhdan, Raskin, Rosenblum, Vershovsky. So these beautiful theorems that tell us the kind of expected field theoretic functoriality for taking mapping cylinders. So the kind of beautiful theorem, the trace theorem that these guys proved, is that if you take the trace of the Frobenius on the category attached to a curve of an algebraically closed field, you get the vector space attached to sigma. It's exactly what the field theory prediction says. So this is one of their main results. Okay. So again, it's a field theoretic compatibility. It's far from, you know, all the kind of rich cutting and pasting you'd like, but it's already a very deep, beautiful result. Does this statement make sense? Okay. All right. So that's all I wanted to say about states. Now, what I would like to get, again, so if you're an automorphic forms person, you say, you're not really doing the theory of automorphic forms before you start talking about things like Hecke operators. Right? So let me now talk about the observables. So, okay, yeah. Oh. Yeah. Yeah, you know, yeah, they're called nilpotent sheaves. The nilpotence is not something one should pay too much of attention of. It's a finiteness condition. So you have to decide, there's the right category of sheaves, and you have to decide what does it mean, the right category of sheaves. And the right category of sheaves is these, in this case, ends up being these Tal sheaves with nilpotent singular support. That's a theorem. That shouldn't be the definition. Really, you want a category of sheaves on which Hecke operators are locally constant as you vary the location. That's the conceptual thing. And they prove a theorem that that's the same. But yeah. No, and that nilpotent, again, I think it's a wrong place to, that's what they're called, but I think emphasizing nilpotence gives the wrong set association. It's a finiteness conditions. They're sheaves that kind of look like fibers of Hitchin, like Hitchin fibers. Yeah, and this is the kind of a good analog of the category of D modules. Yeah. Okay, so observables. So Brian mentioned very briefly his favorite observables, which are the local operators. So let me mention them also very briefly, because I like them too. So the idea is that I'm going to give you all kinds of operations you can do on these automorphic spaces that are labeled by the geometry of space-time. So maybe the plan is I'm going to start with 0 manifolds in space-time, 1 manifolds, 2 manifolds, and I won't get them today probably, but then I'll talk about 3 manifolds. So I'll try to build up. So local operator, what's a picture of a local operator? Again, this is like most things here, things I learned from Dan. The picture I want to have of a local operator is I'm going to think of a 3-manifold cross time. And you pick at some point of time, you're going to make some measurement. And this picture, you like time evolve, you have your vector space attached to the incoming 3-manifold, and you get this is linearized as a map on this vector space. So we get some collection of maps that correspond to points. So here I can tell you where this point happens. So really, maybe I pick a point of M. There's a point of M where this observation happened at, let's say, time 1/2. So I need to pick a point of M. And fixing a point of M, I'm going to get some algebra of operators that acts here. It's easy to see from the pictures that this algebra has to be commutative, just because there's lots of room to move these points around. Everything is locally constant in the position of the point. So in fact, which point I chose doesn't really matter, since my space is connected. And different points will give me, and different operators will commute. So I'll get a commutative algebra that acts on this vector space kind of independent of the point. So what is that commutative algebra? It's something that in the theory of, it's something kind of pretty derived. It's something a little not very much in the classical theory of automorphic forms. But let me just say it concretely, that if I study the space of G bundles on a curve, cohomology of the space, well, if I have a G bundle on the curve, I can evaluate at a point. If I have a point in my curve, I can evaluate a G bundle on that point. And this makes this thing into a module over the cohomology, the G equivariant cohomology of a point, or the cohomology of BG. So there's some commutative ring, the cohomology of the classifying space, and these spaces of automorphic forms are going to be modules for them. Those module structures might not be very interesting in most examples, but it's kind of part of the structure. But you get a commutative algebra. This algebra looks like functions, whatever my coefficients are. Look at functions like on the Cartan, Val group invariant functions like the Cartan, up to some cohomological shift. That's a kind of ring I see here acting. So that's the ring of local operators. Physicists will recognize the Coulomb branch operators from 40 in-mills. Now, in the classical Langlands program, I think these guys didn't appear until I think fairly recently. They're closely related to the derived Hecke algebra operators of Venkatesh. So it's a related circle of ideas. There's Venkatesh-derived Hecke algebra is a more sophisticated object, but it's kind of in the same vein. Okay, so that's all I want to say about local operators. There's something, it's there. You might not care about it, but it fits my agenda. So let's get to the main point.
At some point you were writing like H star.
Yeah, yeah.
You really just meant function.
Well, I really meant cohomology, except that my stack, I had some stack and I had some classifying space of some groups. If I'm looking at complex coefficients and that cohomology is all torsion, then maybe I won't see those operators. But I mean, those.
No, that's fine.
But these.
But I mean, you weren't looking at like the cohomology of locally symmetric spaces.
I was. I wrote H star of locally symmetric. I actually that symbol was on the board. So cohomology of locally symmetric, and this is where Venkatesh's Hecke, derived Hecke actions come.
Well,
Right?
but I feel like you've done some kind of shift. Like basically, I thought
This is the word.
setting you were looking at functions. So like modulus of technicalities, the cohomology was in degree 0.
No, I'm always everything's derived. Yeah.
No,
everything.
But for example, with sigma, when you have sigma, you looked at FQ points. So you really.
But it's as a stack. As
Cohomology for 0, then
yeah.
That's fine.
Yeah.
So it's just function.
Yeah, it's just function.
But for example, you weren't looking at like homology of some spaces because or anything.
I will in a second. It'll be yes. I am.
Yeah. Right. So when you write H star on G.
No, I really mean H star. I really mean H star, except before you put in Stukas, this is a discrete set. You stop saying it, but it's there. It's you should always say H star.
Okay. Okay.
Okay.
I just think of like these derived things as more like actually.
Yeah, everything is cohomology. As Brian said, it's important for this entire game. Everything is always cohomological. Yeah. Okay, so now let's get to the star attraction. The thing that I think makes this theory into a theory is that there's really interesting line operators or one-dimensional defects. These are the main objects of study in this four-dimensional Yang-Mills theory, and they're also the main objects of study in the theory of automorphic forms. Namely, these are the Hecke operators. So what is the kind of picture? Let me draw again my caricature. I have my arithmetic three-manifold, and I'm going to construct an operator on my arithmetic three-manifold. I'm going to let time elapse. I'm going to construct an operator from acting on this vector space now, but this operator now will be labeled by something. Unfortunately, I can't draw knots, however much I try. So this is my knot. Okay. So this is an example of a knot. So what is the idea? So I think of a knot, so as Mignon explained, we're supposed to think in the arithmetic theory, we think of a knot as a prime. So I have let me say, maybe call it V. I have a prime or a place of OF. That plays the role of a little circle. And I'm going to think of an operator, and that again, this operator happens, I'm going to modify my bundles, if you like, at halftime, and by allowing some kind of singularity along a knot. So this is exactly what a line operator is in quantum field theory. I think of a defect where I study the field theory on spacetime with some kind of singularity along an embedded one manifold. And so the idea is that given this, I don't know, I call it L or V, depending on if you think of it as a line or a knot, or a place. So given a line, a one manifold in M, and some labels, I'm going to get a collection of operators on the space of automorphic forms. Now, what are these operators labeled by? There are many of them. And what are they labeled by? They're basically labeled by what can I do? I just told you where I'm doing something. I didn't tell you what I'm doing. So I have to label by what kind of singularity I'm in allowing there. So in quantum field theory, the kind of yoga is that what I could do is I should look at the link of this singularity, which is in this case will be really something like an S2 cross a circle because I'm one dimension higher. I should look at this link of the singularity and I kind of insert some state on this link. So that's a kind of, if you could think of this as some kind of a Bordism from M3 union this tube to M3. If I label this link by some data, those are the data that label all the kind of operators I can insert there. So there's some set of labels, and I'll tell you what they are. But first I wanted to convince you that, that this relates to, Well, there are two key things to say is that still I have a lot of room. I still have a lot of room. If I take two such operators, there's enough room to move them around each other. They still commute. So the collection of operators I get this way still form a commutative algebra. So that's a kind of these key thing. This vector space comes with a big commutative algebra and that acts on it. And what is that commutative algebra? Let me draw this same picture in a way that will be a bit less offensive to number theorists. Let me like puncture this and blow the air out. So take this picture and like collapse the air. I'm going to shrink it like an accordion. And then what do I get? I get a picture like this. Here's my M. Now, nothing has happened except around this knot. And kind of when I shrunk the air out, I still have some little kind of bubble around this knot. Okay, how do I draw this? Okay, I can't really draw very well. So it's basically a non-Hausdorff kind of thing. I take two copies of M3 and glue them around the complement of the knot. That's the kind of picture I have here, right? So I have this kind of M3 union over M3 minus the knot M3. And this is some kind of, it has inside of it two copies of M3 on the left and on the right. You think through what this operator is doing, this becomes exactly a Hecke operator. The knot. Let me just do a single one. But you could, sorry, there I was trying to explain commutativity. You could do it for many at a time if you'd like. But the point is that the operators you get this way are naturally Hecke operators. You're studying a G bundle on M3, and you're modifying it. You have two G bundles, which are identified away from this singularity. Or, two elliptic curves that differ by p isogeny. That's kind of the arithmetic version. So this is exactly what Hecke operators are. You study this locally symmetric space. It has a lot of interesting correspondence on it that are labeled by a prime and some extra data at them. So these are exactly Hecke operators. This is how Hecke operators appear in the.
Like, is it coming from the category that you were acting for this two-dimensional thing, or is it?
So there's several things. Yeah, so there's several levels of structure. First of all, I'm claiming that in any topological field theory, if I have a four-dimensional topological field theory and I look at the value in a three-manifold, I'll get a commutative algebra acting on it. That commutative algebra will look like the value, if you like, on S2 cross S1. It look like there's a vector space, which is the field theory evaluated on something like S2 cross S1. That vector space will have a commutative algebra structure, and it'll act on this vector space. That just follows from the axiomatics of if you had an honest field theory. Of course, this is a make-believe story, right? If you're in a setting where you have an honest topological field theory, this is something you just easily calculate from the axioms of topological field theory.
That uses value.
That'll be the labels of the operator. I haven't told you what Hecke operators are labeled by yet. I'm just saying that it follows axiomatically that you'll have some collection of operators that I'm calling Hecke operators, and they form a commutative algebra and they act. Now, what's special about the theory of automorphic forms is I know what those operators are. Of course, this could have been trivial. It could be just, there could be no Hecke operators. There could be theories that have no line operators in them. In the theory of automorphic forms, this is something interesting. This value is calculated by the Satake isomorphism. And the Satake isomorphism calculates it for me exactly what this space that I'm trying to evaluate is. I'm calling it schematically S2 cross S1. And it says it's just the representation ring of the complex of the Langlands dual group. So it identifies this ring as some, we'll talk about, I don't want to talk anything Langlands dual today, but it gives a name for what this commutative ring are. So the labels you can put here, the things that you can label this by are representations of the dual group. Yeah, so the category of S2 is going to be the category of representations, and those are the actual line operators. So here I'm looking at loop operators. I'm looking at the traces of these line operators. Yeah, so kind of more fundamentally, I would be interested in a line, but here I'm looking at the loops. Yeah. So the importance as you look at operators, yeah, these are exactly the 't Hooft operators. So yeah, so gauge theoretically, this is exactly the picture of an 't Hooft operator. I'm allowing my gauge fields to have some singularity along a line, and I'm labeling that type of that singularity by an solution of the equations of motion on that linking sphere. Which is, yeah.
So you can label these by states on the boundary of the tubular neighbor.
Yeah.
Doing on the left, but you can also do with damages and have the local.
Yeah. So exactly. Yeah, so the value on S2 cross S1 is just the trace or K group of the value on S2. So this is a category. No, oh, sorry, this underline. I don't know. For me, rep is always a category. I'm trying. What is the name for the representation ring? I don't know. This is supposed to be the ring.
That's the way. Oh,
R. Oh, there we go. That's the name. R. R. This is the representation ring, which is the K group of the K. It's only a vector space. It comes as the K group or trace of the category of representations. Okay. So so this tells you. So this is kind of the main feature of the theory of automorphic forms, is that these vector spaces carry big action of commutative rings. These commutative rings you have this commutative ring at every prime, and they all commute, and they're labeled by a particular data, which is where the Langlands correspondence kind of starts. Okay, so yeah, that's right. So the category AG of S2 is the geometric Satake correspondence, says that this is the category of representation of the Langlands dual group, up to some derived stuff, and that derived stuff will play a big role by Friday. So let me not get myself in trouble. So it's a derived enhancement. It's an interesting derived enhancement of this category, not the naive one, not the obvious one. So it's an interesting derived enhancement of this category, and this is its trace. Okay. Okay, so that's an example of, so that's sort of, I think, the main, these line operators are kind of the main feature in this four-dimensional Yang-Mills theory. They're also the main feature in the theory of automorphic forms. And what we're going to try to do is now later spectrally decompose. We have a commutative ring, and we can try to spectrally decompose them, but I'm not going to talk about that today. Since the word Stuka was mentioned, let me just draw some more pictures. So I just want to give some more repertory of pictures you can draw. So for example, if I have a curve over a finite field, I can also take these same line operators, but draw them in a different way. So I could take this picture I drew before of a Riemann surface or a surface bundle over the circle. That's my picture of my three-manifold, and I can draw the same loop operators, the same exact defects, but now I'm going to have them go this way. So I'm not drawing space-time here. I'm just drawing space. Right? I'm just drawing my arithmetic three-manifold. I'm not drawing time. So here I'm saying there's a new, if you'd like, it's a new arithmetic three-manifold. It's this three-manifold, which is the curve over a finite field, labeled by some defects. And what are these defects? Well, they're labeled. I need to give you some points. I need to give you some loops here. These are points defined over f of q. So I need to give you some FQ points, and I give you some labels. That's a V1, V2, V3. These are X1, X2, X3. And I'm supposed to look at, so I can look at what the automorphic theory attaches to this picture. Okay? So that's a vector space that's labeled by a curve over a finite field, plus some choices of points, and these labels, which are representations of the dual group. And this is exactly the cohomology of the space of Stukas with a bunch of legs. So that's a name for this. So if you don't know what Stukas with legs are, that's what they are. So this is, yeah. So it's a cohomology of the space of G Stukas with legs at these points, x1 up to xn. So that's a name for these singularities. No, it just means that I'm thinking of the picture as being, the VI is the label of a singularity, right? The singularity, so here I have FQ points. An FQ point means a circle here, right? It's a section of the fibration. So I give you an FQ point, that's a circle, and I'm just labeling that circle by one of my defects. Well, because I want to tell you that I have some interesting, my arithmetic three-manifold has interesting circles in it. And these circles are ones I don't have an analog in the number field situation. Exactly. They're living over Frobenius. And what is a Stuka? A Stuka is like a G bundle. It wants to be a G bundle defined over FQ. but it fails. To be a G bundle defined over FQ, it would be invariant under Frobenius. It would be isomorphic to its Frobenius twist. It fails exactly at these points by these amounts. So this is a measured way of saying a bundle that's almost defined over FQ. And this is Drinfeld's thing. Stuka means thingy, I think. Yeah. Yeah. Yes. This happened like 2 years before ADHM. So this happened a couple of years before ADHM, but yeah, same D. But yeah, yeah. Anyway, yeah. It's locally constant in the choice of points, right? A topological field, everything is locally constant in the choice of points. I mean, it depends on the choice, and then, but then there's some monodromy. I mean, there's some. Yeah. Yeah. Well, the OPE is this. This is the representation ring of this group. That is the OPE structure algebra. These guys satisfy the OPE algebra, which is the representation ring of the dual group. But this is really behind Vincent Laforgue's point of view on Langlands correspond over function fields. Okay.
Well,
yeah.
I don't quite understand the thing in the parentheses. When you say a defect, like if this was a manifold, what would you?
So yes, and then telling you what happens there. So defect means I have an embedded submanifold of some dimension, and then I'm allowing something interesting to happen there. So if you think of a field theory as some kind of functor on some category of manifolds, a field theory with defects means a functor on a category of manifolds labeled with embedded submanifold and some labels on those. So I'm extending the value of the field theory to allow manifolds with defects, a manifold with an orange loop in it. So now I have pictures not just manifolds, but manifolds with orange loops. This is not really a new thing. It's built into the structure of the field theory. The label, the things that could be here are elements of this vector space giving the link of this.
But you would extend the axiomatics.
But yeah, the point is it's already built in. Okay, the axiomatics of yeah, if I was to define the axiomatics of an arithmetic field theory, it would have to include this. In the honest topological field theory, it's already built in.
Meaning you could, that is natural.
Yeah, there's a natural way of extending this, and yeah, there's a beautiful theorem of Jacob Lurie that classifies exactly what kind of defects you can do. Okay, so and so just to say that a lot of the features of the theory of automorphic forms, this is an interesting feature of theory of automorphic forms over function fields, and it again is sort of completely natural from the field theory picture. I completely forgot when I started, and a while ago. Okay, okay.
Yeah, well,
okay. Okay. So that's not bad. We're about halfway, so that's good. Let me just say let me just preview next time. So I've talked about local operators. I've talked about loop operators, line operators. What I'll do next time very briefly is continue with Brian's comment about surface operators and how they have to do ramification. I'll talk about what level structures in the language. So of course, with automorphic forms, level structures are important, how those correspond to levels, to ramification or surface operators. And then my main goal is going to be talking about boundary conditions, codimension 1, and that's going to be the theory of periods of automorphic forms. So next time I'll try to talk about the theory of periods of automorphic forms, and then do the Langlands dual, how everything gets dualized. Okay. Yeah. Okay. So tomorrow there are no talks tomorrow. On Wednesday, Brian and Mignon and Brian are speaking, but the times are on the webpage, and it's way too complicated. And then Thursday, I think Mignon and I are speaking, and Friday, Brian and I are speaking. Right. Thank you.